This is a Module 4B video on stereoselective Diels-Alder cycloadditions. To review the definitions of stereoselective and stereospecific, a stereoselective reaction is any transformation that favors one stereoisomer over others. A stereospecific reaction relates the stereochemistry of product to the stereochemistry of the reactant by the mechanism of that reaction. Diels-Alder cycloadditions are stereospecific reactions. The stereospecificity is the origin of the stereoselectivity that is observed. As we scroll down the page, we can compare the products that arise from the reaction of 1,3-butadiene with a trans alkene, specifically the dimethyl ester of fumaric acid, versus the cis alkene, the dimethyl ester of maleic acid. I will draw the structures of the products. In the Diels-Alder transformation, if the substituents are trans in the reactant, then in the cyclohexene product, the ester substituents will be trans. To be completely unambiguous, I will generally draw all of the atoms that are attached at chiral centers. In this case, showing the hydrogen atoms at the chiral centers. However, the opposite enantiomer of the cyclohexene product will also be formed. The answer will be completely correct if you draw just one of the enantiomers and use the symbol plus minus or otherwise indicate that a racemic mixture of products has been formed. Although if you do draw both enantiomers, technically, then the use of the plus minus term is redundant and could be confusing. For the cis isomer, the cyclohexene forms with the esters that are cis in the alkene, being cis on the substituted cyclohexene. Once again, the diene and the alkene can react from two different faces. This is the mirror image form. But notice that these compounds have an internal mirror plane of symmetry, so that this stereoisomer is a meso compound. Therefore, these two structures are equivalent. The Diels-Alder cycloadditions that are shown are diastereoselective. The individual diastereomers of the alkene reactant give different diastereomers of the cyclohexene products. However, the reaction is not enantioselective. Both enantiomers are formed. But because the stereochemistry of the products is linked to the stereochemistry of the reactants by the mechanism, this is a stereospecific reaction. In fact, stereospecificity is strong evidence for a mechanism that proceeds in a single step without a reactive intermediate that could cause the thermodynamically more stable isomer to be preferred. Turning to the next page of the worksheet, Diels-Alder cycloadditions have an interesting property in that the major diastereomer is often the diastereomer that is not thermodynamically favored. The isomer, which has the alkene and carbonyl groups cis to each other, is slightly higher in energy than the isomer, which has the alkene and carbonyls trans to each other. But the reaction mechanism leading to the endo product has a lower energy barrier, so that the reaction leading to the endodiastereomer proceeds faster than the reaction pathway leading to the exodiastereomer. The mechanistic description is depicted in the textbook on page 888, and I'll leave it to you to read through that discussion, as it is more complicated to depict for maleic anhydride plus cyclopentadiene. The rest of this page describes instructions for drawing, and in the case of this semester, for recognizing which isomer is endo or exo. I will show this on a blank screen, but please follow along with the instructions on the worksheet. Following the instructions, I will first show the diene reactant, and I will draw in all of the hydrogen atoms to be unambiguous. For the endodiastereomer, for the reactant maleic anhydride, I first draw the alkene using a different color. Then I will add the electron withdrawing groups where they are tucked under the diene, close to the pi bond that will form in the embedded cyclohexene. I've actually marked the bonds that are going to form in light green. We can then unfold the structure, drawing in the bonds so that every substituent facing to the right in this initial scheme will be on top in the product. And then I'll draw in the remaining hydrogens. This is the endodiastereomer. I repeat the process leading to the exodiastereomer. This is easier to draw, even though it is the minor product of the cycloaddition. Once again, I will first show the diene, then underneath I will show maleic anhydride, but now flipped 180 degrees so that the electron withdrawing carbonyls are not close to the developing pi bond. After unfolding the structure to reveal the cyclohexene with bridging group, once again, all substituents that were depicted to the right in the previous diagram are on the top side of the exodiastereomer. As before, I draw in the remaining hydrogens to be unambiguous. Turning to the final page of the worksheet, the evidence is that the endo selectivity is not very high under thermal conditions. In fact, there's probably some thermodynamic equilibration that is occurring. But in the presence of a Lewis acid, which coordinates to the basic nitrogen of acrylonitrile, that lowers the LUMO energy to react more rapidly with the HOMO of the diene, so that the kinetically favored endodiastereomer is favored. During the class meeting, we'll work through the process described on the previous page, to create structures for the endodiastereomer and for the exodiastereomer. This concludes the Module 4B videos.